What is up, Flutter devs? Today we're going to make some noise with Flutter processing, specifically Perlin noise. Let's jump into it. Rather than me explaining what Perlin noise is, I want to start by showing you something that is not Perlin noise. I want to set the context here for our conversation. We're all familiar with random number generators. But what does it look like if we paint the screen using a bunch of random numbers? Let's find out. Let's paint every pixel with a random number, a gray value from white to black, but it's random. This is going to require us to loop through every pixel. So we have to load the pixels, paint the pixels, and update the pixels. Let's set up that little framework here, and then let's look at what it means to paint random numbers as gray values. We're going to load pixels so that we can paint them. When we're done painting them, we need to update them. And then we're going to say for column from 0, where it's less than our available width. And then inside that loop, we are going to go through all of the rows while that's less than height. And we're now dealing with a specific pixel. We're going across the screen and then down. We are looping through every single pixel on the screen, in this case a 400 by 400 canvas. And now we want a random amount of gray. For that, to make something gray, we just need the red, the green, and the blue to all be the same value. We need to generate a random value for each color channel. It needs to be the same. So let's say gray amount equals, we already have random in here. We will generate a value between 0 and 255. Each color channel, red, green, blue, can have a value between 0 and 255, so that's what we generate here. We just need to make sure that red, green, and blue all use this value. So we can say color equals color from ARGB. We want the alpha to be 255 fully opaque, and then we're going to pass in the gray amount for the other 3 channels. Because the value is the same, sorry, it needs to be 2int. In fact, we want to floor it because 255, well, I take that back. Let me remind myself whether this is exclusive or inclusive. I always forget. So next double, I think, is exclusive. Yeah. So what we actually want here is 256. And then we're going to floor it so that if we get like 255.5, we drop down to just 255. So a number that could be 0, could be 255, or anywhere in between. Because we use the same value for red, green, and blue, the color is going to end up being gray. Then we want to paint this one pixel with this one color. We will call set. The X value is the column, the Y value is the row, the color is the color. And I'm also going to turn off looping so we can see a single frame. Let's see what this looks like. There we go. Looks kind of like noise. It looks like the static that you might see on your television screen. This is what I'm referring to generally when I say noise. Noise can refer to a random number generator of different types, because if you actually paint what those random values would look like pixel by pixel, you end up with some kind of noise on the screen. So they're kind of the same. This is probably what you think about when you think of noise, and yet really all we've done is sample a random number generator. Now, the reason that this noise is so chaotic is because it's truly intended to be random, as in the next value has nothing to do with the previous value. But there are many cases where that's not what you want. We're not going to create any particular simulations or exotic effects in this video, but there are simulations and effects where you do want randomness, but you don't want the value to be too different from the one that came before it. The canonical example is something like generating terrain. Think about the 3D scenes where you generate mountains and you generate like oceans or lakes. So essentially you're generating random structures in two directions from the baseline. You want it to be random in that you don't want it to be predictable where the hills and the valleys and things appear. But you can't go from, Mount Everest to the bottom of the ocean 1 pixel over. You need gradations overall. You need the next value to be somewhat similar to the value that came before. And so there are other types of noise that have that kind of property. One of those types of noise is Perlin noise. And so that's what we're going to explore here today, or we're at least going to look at an example of it kind of sampled on the screen like this. Now also, let me show you one cool effect. If we don't turn off the looping, we're going to generate frame after frame of this. And so now it really does look like TV static, right? So if you ever wanted to capture a little video clip, maybe you want to use something in After Effects or Premiere, you want some kind of noise overlay, you could actually come in here and generate your own pretty easily. And of course, you control the dimensions here. You could make this 1920 by 1080 if you wanted to. It would just take a bit longer to generate that noise. But even that little effect, I think, is kind of neat that we can get that from processing, or in this case, Flutter processing. But to investigate Perlin noise, let me go back to no loop. So we're back here with just a single frame. And I want us to paint a single frame of Perlin noise. Now, there are some algorithms for Perlin noise floating out there, and we could have tried to copy it and port it into Dart. But I found this package on PubDev, which is fast noise. And you'll see here that there are a number of types of noise. Remember, I said there's not just one or two types of noise. There are many. But one of the ones supported by this library here is Perlin noise. So we should be able to integrate this library into Flutter processing and then use the implementation here of Perlin noise and just paint the values when we want to. Here, by the way, here are some visual results of different types of noise. This first one is cellular. I don't know what the mathematics are behind that. Then this is actually an example of Perlin noise. Ours is going to look a bit different because I think we're going to zoom in more on our sampling. Also, the frequency here I think may be different than ours. But this is an example of sampling Perlin noise over a certain size. Here's a simplex fractal. Again, I don't really know the mathematics behind any of these, but these are all different algorithms for generating noise. Not all noise is static noise. So let's pull this in. So fast noise 101. Let's bring that into the dependencies for this project. Now we're working in the example app, but eventually we want Perlin noise to be available to anyone using Flutter processing. So we're coming into the main package level PubSpec file, and under dependencies, we're going to say fast noise. What did I say? 101. 101. Okay, save that. Run pub get. And then let's think about what has to change here. We still want to paint every pixel, and we still want to paint with gray values. The only thing we want to change is how we generate that gray value. So right here where we say gray amount, we want to use a different approach. Somehow we want to say gray amount equals some Perlin noise value. Okay. With that library, what we can do, we need to instantiate a Perlin noise object, which I will do up here in the state make it a local member of the state object. Call it Perlin noise, and that's going to equal Perlin noise. And I'm not sure why that's not auto-completing for us. Okay, well, that solved it. And then inside of Perlin noise, we're going to say octaves 4. You don't need to understand what that means. In fact, the default's probably fine, but I think the default in processing is 4 octaves. And then down here, we want to say Perlin noise And then we want to call get Perlin 2. This is two-dimensional Perlin noise because we're sampling in 2 dimensions, right? And here's another thing to keep in mind. You might think that one-dimensional noise would be fine because in a sense, what we had before was one-dimensional, just one value after another. But it's not just the noise values along one row that need to look similar. The noise values as you go down need to look similar too. We actually, that similarity concept that I mentioned where the next part is similar to the previous part, we actually need that to be true in 2 dimensions so that when you look at this noise as a picture, it makes sense as a picture instead of a bunch of unrelated rows of pixels. That means we are generating 2-dimensional Perlin noise. The X value is the column, the Y value is the row. Now what we're going to get back, and actually those probably aren't good X and Y values. I'm instead going to change those to a %. When we sample Perlin noise, there's a certain coordinate space within Perlin noise, or at least, our pixel values don't mean anything to the Perlin noise generator. So we're going to operate off of a percentage. We'll say width % equals column divided by s dot width, and then height % equals row divided by s dot height. Now what we're going to get back, I'm going to change that name because this is the Perlin noise value. This value is between -1 and +1, I believe. So our gray value is actually going to be Perlin noise value +1. Now it's between 0 and 2. Then we're going to divide it by 2. So now it's between 0 and 1. And then we're going to multiply that by 255. And we are going to round that. Yeah, I think that should work. Okay, so if I didn't miss anything, that should give us 1 frame of Perlin noise. It's possible that these percentage values are going to give us, essentially we can zoom in and zoom out of Perlin noise. And so based on how much of a percentage difference we move every pixel is going to determine how zoomed in we are on the noise versus zoomed out. Maybe we'll play with that in a moment, but let's just see what we get. Okay, it's all gray. So my guess is these percentage values are not a great way to increment. So let's instead try this. Let's say we will have double X equals 0, double Y equals 0. And for every pixel, well, first we'll pass in X and Y. And then at the end of every row, we'll increment the Y value by just like 0.1, very little amount, and X by 0.1. Because I believe that the resolution of the noise is based on the difference between the values that you pass in here. Any one particular value doesn't really matter, but the difference between that value and the next one, I think, makes a difference. And I still don't know, I can't remember now with this package what kind of difference we want. Let's see if this gives us a better image. Okay. So you can see that we're getting values on a row that are different, but, well, going across the columns gives us different values, but then going vertically, we're repeating the same row over and over again. So let's see why that is. So for every row, we're incrementing Y. For every column, we should be incrementing X. So maybe I'm just misreading something here, but let's print this out. So it seems to be changing both of those numbers, although the Y value is going way too high. We need to reset the Y value right here. Or I guess we can set it down below where we increment the X. When we increment X, let's see, what are we doing here? So we're doing all the rows, we're going down and then over to the other column. We increment Y all the way down a column, then we increment X over to the next column. We need to reset Y back to the top, and that should give us the correct kind of mapping of pixels to the two-dimensional space. And let me take the print statement out in case that's slowing it down. Says it's performing hot reload. Okay. All right, we're getting something here. So now there's some kind of gradation here. Let's see if, I don't know if we need to zoom in or zoom out. Let's make this 0, 1 and see what happens. I think that may have gone the other direction. Well, we were already doing 1, incrementing by 1 before. Well, now we're getting a little something. Okay, so you're starting to see some noise in here, right? And so when I'm changing these X and Y differences, we are essentially, in fact, hold on, let me get a metaphor for this. Okay. This sponge right here, and unfortunately it's kind of getting washed out in the light, isn't it? This sponge is Perlin noise. Take the top layer of this sponge, and that's essentially what we are graphing or charting or sampling, however you want to look at it. The question is, what portion of this sponge are we sampling? Are we sampling a tiny little square up here in the corner? In which case there's very little difference. It all kind of blends together if we're zoomed way in. On the other hand, if we zoom out and we capture a lot more detail, then it looks rougher. There is more detail. We're seeing more change. But the face of this sponge, you can think of this as the Perlin noise space. And then based on how much we increment our X and Y into the Perlin noise function, it determines, are we taking a tiny little sample up here? Are we adding very, very small numbers together and looking at this tiny little corner? Or are we adding larger numbers and looking at a much bigger area that has more detail? That's what we are seeing here. Let's see what happens if we increment by 1. Right, we're seeing more. Now, I don't know why. I guess because we were going by percentage earlier, not by pixel. So going by pixel actually may have been a better option after all. But now we're starting to get more noise here. Let's go 5. All right, and now you can almost start to see something like what we saw here in the package description. There's maybe some different coloring going on here, and that frequency factor might change things a little bit, but you're starting to get that sense, right? Now, that's actually quite a bit of detail, but still quite blurry. Maybe some of those other settings in Perlin noise could change that. One thing is that octaves will impact the amount of detail. So let's double that to 8. Let's see. Let me actually I have to hot restart for that to take effect. Okay, didn't really see much of a difference there by increasing the octaves. Let's see what else we have here. Seed frequency octaves, gain. So gain will have an effect as well. Gain is how quickly we kind of slope away So how quickly something changes. Let's increase that by 50%. Let me hot restart. Still doesn't look much different. I mean, maybe we're too zoomed out now. Let's go to something extreme like 100%. Yeah, I'm not convinced that that's actually taking effect. Let's just, I don't know, this might mess up how it's rendered if we're recreating it every frame, but let me just see what happens if I put it there. So I would have expected gain of 100% to make a massive difference. Well, in any event, I may be forgetting something here or missing something, but hopefully you get the general idea. As a reminder of what we had before, here's totally random noise where every value is disconnected from other values. It's just a bunch of roughness. What we have now is noise, random values, where the next value in any direction is similar to the previous one. Not the same, and sometimes it changes more than others. But in any locality that we're generating here, there is some relationship between the previous and next value, so nothing ever changes too quickly. You can look at this and see kind of imagine this is a topical representation of a landscape. The light values are high tops, the dark values are like lakes, rivers, whatever. So you can see how some version of this algorithm might be used to generate some terrain. And we'll also do some exercises in the future where we make use of Perlin noise for simulations and for some rendering purposes. But this here is Perlin noise processing from an API standpoint has a method called noise, which is intended to generate Perlin noise. So in the next video, we're going to come back, take what we've learned here, take this package that we found, and we're going to implement the processing APIs for Perlin noise in the Flutter processing package so that developers have access to that. Hey, it's me from just a moment in the future, realizing I forgot one of the cooler things that we can do with Perlin noise. Remember the sponge and how I said we're sampling the face of this sponge, and that's what creates the effect that we were seeing on screen? Well, what if we could like shave off one layer of the sponge after another and look at layer after layer? Or like, what if we could move through the sponge in the third dimension, in the Z dimension? Perlin noise actually allows us to do that, because Perlin noise doesn't just generate related values in 2 dimensions on one face. Perlin noise really is like a mathematical space that looks like a sponge, and we can move through that third dimension. Let's do that. Right now we're showing just one slice of the sponge. First, I'm going to remove the no loop, so we start looping again. Now this isn't changing because I think the same seed value is always being used. So it's always the same random sponge. What we're going to do is explicitly move through the Z index. Here's how we're going to do that. We already have X and Y, and we already control those pixel by pixel. The Z value is not some other pixel. The entire frame that we paint is at one Z level, and then the next frame should be at the next Z level. So the Z value has to change from outside the draw method. We will say double Z equals 0. And we will increment Z just like the other two. We will say at the end of the draw method, we will say plus equals 2 because we're currently incrementing X and Y by 2. But then up here, instead of get Perlin 2, we're going to say get Perlin 3 and pass in Z. And now let's see what happens. Okay, can you see it start to change there? I'm going to make the canvas smaller because I think what we have here is we're just painting too many pixels using software. So let me reduce this to 200 by 200 and we'll get some better speeds. Okay, so hopefully that's a bit easier for you to see. It's smaller, but it's faster. And what it looks like here, it's almost as if we have a microscope that's out of focus and there are little bacteria or things moving around under the microscope. But the cool thing is, just like the X and Y relationship, the X and Y values are never too different. The Z values are never too different either, which gives us the appearance of motion, because motion is nothing but small changes over time. Therefore, small changes in the generated noise look like some kind of motion. Let's see what happens if we really crank up that Z value a bit. Let's make it like 10x more. Okay, so now we're getting a rather jarring experience because we're jumping a lot further into that sponge. The front face of the sponge might be very different than the back face of the sponge. Here we're jumping very far into the sponge. Let's go back to like 5. Okay, so now we're kind of at a healthy medium. We're getting some good changes, some good motion. So it's not too fast, not too slow. We're not necessarily jumping too far. But of course, you can play with that value however you want. But that's what I forgot to tell you a moment ago. We get that kind of motion effect. And this is one of the reasons, not only is a two-dimensional Perlin noise is still useful for generative art and simulations and things like that, but three-dimensional Perlin noise is like extra useful because you get this ability to have random stuff impacting motion or impacting gradients or whatever. Without something like Perlin noise, how would we do that? The random number generator isn't going to cut it because that's just static noise. So with that, we are now for real done. In the next video, we're going to implement the processing APIs in Flutter for Perlin noise. So I hope to see you over there.